Mike? Okay. Today is the big day that we've been building up to. Very important stuff. So try your best to pay attention and follow, and if you're having issues, watch the video tonight, which is this video. So today's Invader Problems. What makes an Invader problem is we are adding a strong acid or base to pretty much anything we've already studied. You can add strong acids and bases to strong acids and bases, weak acids and bases, salts, or buffers. So what I want you to think of is I want you to think of the strong thing that's being added as an alien, and the alien is attacking Earth. And so the first step of every one of these problems is what I call a war, and we do it in something called a stoichiometry table. A stoic table is a little bit different than a rice table, but we're going to figure out who wins the war, and then whatever is left over, whatever the casualties of war are, those are the ones that are going to determine what the pH is after. So this list here that I have will make a lot more sense to you to read through after we actually work a problem. Sometimes the best way to learn this is just to jump in. So we're going to start, and we're going to go to, yeah, and I knew I did something wrong. Always make my life difficult. Let's go to here. I need to be able to get to that button. All right, so first problem. 125 mils of 0.525 molar HCl is mixed with 125 mils of a buffer system, which is 1 molar in acetic acid and 1 molar of sodium acetate. Find the pH of the final solution. This is the first three problems I made up, they're very simple and clean just to get used to the process, and then we're going to work some actual AP problems which have a lot more words and are going to make your eyes cross. For this problem then, we first identified, you see how we're adding something strong, HCl, okay? Whenever we're adding something strong, we're only really adding an H plus or an OH minus, and we're adding it to this buffer system. So thinking about this buffer system that we have, we've got acetic acid and sodium acetate happily floating around doing their thing. That's what I was saying was Earth, and it's going to be attacked by H plus. So when we write our equation, this is the hardest part for students, this very, very first equation. When we write our equation, we start with the invader. The invader is always a reactant. Which part of the buffer is the invader going to react with? It's not going to react with both of them. It's an acid. It can't react with the acid. It's going to have to react with the ion. So we're going to get AC minus. Now because this is a war, the war has an end. So our arrow is single-headed to the right. Okay? It's not equilibrium. It doesn't go on forever. It has an end. So what do we make? HAC. So to figure out what we have left over after the war, we have to go to battle. And in our stoichiometry table, you have to put things in this stoic table in moles. They've got to be in moles. So you're going to get really good at taking molarity and liters and finding moles. You just take molarity, multiply by liters to find moles. So we have 125 mils of 0.525 molar HCl. So what do? 0.125 liters times 0.525 molar HCl, and what do we get? 0.0656 moles of H plus. You don't have to show work for that. Just do it. And I'm hoping you're to the point we don't have to do your dimensional analysis to get from mils to liters. We got to be past that, hopefully. AC minus then, we have both HAC and AC minus in the buffer, so we're going to have starting moles of each of those. It looks like they're both 1 molar, right, with 125 mils. So what's our moles? 0.125 of each of these. So we have 1.125 and 0.125. Again, the stoichiometry table has to be in moles. So now we look at it like a limiting reagent. One of these is going to run out first. Which one? H plus. Poor alien's going to lose this battle. We're going to lose 0.0656. For every one of those, we lose that same amount because of the mole ratio, plus 0.0656. That's how much is gained when we do our reaction. Lose, lose, gain. And so we're left with no more alien. The H plus is gone. And what do we have left here? How much AC minus? 0.0594. And how much HAC? 0.0656. Now, in this particular case, because, oh, well, hold on, I'll go back. That's not right? Oh, it can't be right. This is where it shows you I don't pay attention. I literally just write and talk. So what do we have there? Point what? 191. Okay. So this is how many moles we have left over. In order for us to continue, we need to now take stock of, after the war, what the casualties are and what's left over. We have HAC and AC minus now strolling around in a beaker together. There is no reactant and product anymore. These are just free floating in a beaker. What kind of system do we have left over? Buffer. So if we have a weak acid and its conjugate left over, we have a buffer system left over. Now we start and we solve the problem just like it's a buffer problem. The only issue is this is moles. When we do rice tables for the weak acids, when we do rice tables for hydrolysis, when we do negative log of something strong, they always have to be what? Not in moles, in concentration. So in this case, what is our total volume after the war when you mix them? 0.250. But do you see how, if we're going to be using Henderson-Hasselbalch, we really don't need to do this division specifically in the case of buffers only, because look at Henderson-Hasselbalch. pH is equal to the pKa plus the log of the concentration of the ion over the concentration of the acid. Do you see how these we're dividing both of those by the same volume? So it wouldn't change the ratio if we just put in the moles. This is the only time, though, you don't have to convert it to molarity. Otherwise, if it's a weak acid left over and you have to use a rice table, or if it's anything else, you have to convert those moles to molarity. So pH is equal to the negative log. The Ka of acetic acid is 1.8 times 10 to the negative fifth, plus the log. What do y'all want to put? Do you also want to find the concentration? Do it that way? What's the concentration of the AC ion? 0.2376 divided by the concentration of HAC, 0.764. All right, so it looks like we have 3 sig figs and everything up there. So to 3 decimal places, what is our pH? Can I get a second on that? All right. So that is the pH of that solution. Any questions? Does that seem pretty straightforward? Yes, no? Oh, gosh. All right. Moving to the next one. "125 mils of sodium hydroxide is added to 125 mils of 0.5 molar acetic acid. What is the pH of the final solution?" So same thing here. We're going to go ahead and just make an equation. This equation is easier because we don't have a buffer to choose which component is reacting. That and that, if they're going to react, you just add them together. So our Invader is OH minus, and it's going to react with what? Acetic acid. Single-headed arrow, because all wars are going to come to an end, and we make AC minus plus water. In the Stoic table, just like in the rice table, we just don't even deal with the water. So we got to be in moles. So 0.5 molar sodium hydroxide times 0.125 is 0.0625. Acetic acid, 0.0625. Do we have any acetate this time from the get? No. So how many moles are going to react? 0.0625. But this time we're going to gain 0.0625 moles. So we have nothing here Nothing here. Uh-oh. The war is over, and this is all we have left. What kind of problem is this left over? What do we think? It's going to be something we've already done. Is that a strong acid or base? No. Is that a weak acid or base? Not specifically. It's salt hydrolysis. All right? So remember, that is no longer a product. It's literally by itself floating around after a war. Imagine a war, and Westlake were the only people to survive. We walk out in the streets, everything's destroyed, but we would be free to do whatever and repopulate the planet and all that kind of stuff. That is, don't even want to think about that. Anyway, that's what's going on with the AC minus. So now the AC minus is going to, we need, before we can continue, you've got to convert that to molarity. So what is our total volume? 0.250 liters. So our molarity of HAC is, of AC minus, I'm sorry, 0.250 moles per liter. All right, so now we do like we do with any hydrolysis problem. We take the ion, and what do we do to it? Add water, and we're going to get HAC plus OH minus. So, same thing we did last unit. So if you didn't know how to do it last unit, it's not going anywhere. Minus X, plus X, 0.250 minus X, X, and X. So we get here our K what? When we write our expression, KB is equal to HAC times OH minus divided by AC minus. Well, they never give us the KB in a hydrolysis. They're going to give us the Ka of acetic acid. So we're going to take the Kw, 1 times 10 to the negative 14th, divided by the Ka of 1.8 times 10 to the negative 5th. And that's equal to, we're going to trump this X, negligible. And we're going to get X squared over 0.250. So our X then, which is equal to our OH minus, is 1.79. Hold on, I'm going to make this whole screen a little bit smaller because it's frustrating me. 1.8. 1.18 times 10 to the negative 5. And we don't worry about sig figs till our last thing. Now everything, oh, I hate when I do that. Just pretend they're all 3 sig figs. So POH to 3 sig figs to 3 decimal places is 4.93. Give me 3 decimal places. 929. pH then is 9.071, and that is what they were asking for. All right, so you see the pattern? You have the war, and you see what's left over. So we're going to do one more. So far you've had a buffer left over. Here we had a salt for salt hydrolysis left over. Potentially you would have the alien win, or you could have the weak acid or base left over. If you have the weak acid or base left over, you do the same thing. You just take your weak acid or base concentration, put it in a rice table, do the same. Strong is going to be a little different, and that's what I want to talk about with this next problem. 200 mils of 0.5 molar NaOH is added to 125 mils of 0.5 molar acetic acid. What is the pH of the final solution? So this is an invasion. What is our invasion equation? Notice the rhyming of that. The invasion equation is the hardest thing for people to write. What do we start with? OH minus, and it's attacking HAC, and single-headed arrow, we're going to get AC minus plus water. All right, how many moles of OH minus do we start out with? 0.5 times 0.2? 0.1 moles of this dude. And then HAC is, again, 0.0625 and 0. So how much are we going to lose? Who's going to run out first this time? Yeah, our poor little earthling is going to get taken over by the aliens. All right, 0.1 minus 0.0625. 0.9375. 0.0375. All right, so here's the thing about this situation. If you have any of the strong invader left over, strong wins. Due to the fact it's a strong base compared to that little bitty weak base over there, this is going to mathematically have the strongest importance on the pH. This will not add enough to matter, so we only utilize that information to find the pH. So we take those moles. What do we do to those moles? Convert to molarity by dividing by 0.325 liters. So what is our concentration of our OH minus? .115 moles per liter. So if I have the concentration of OH minus, how do I go about finding pH? Just do negative log to get POH to 3 decimal places. What do we get? Therefore, that's POH. Therefore, our pH then is equal to... Does it make sense for us to have a basic pH when the basic alien took over? Yeah, it does. Make sense? All right, now let's take a look at what these puppies look like when they're in AP format and how they're built. So, number 8. What is the pH of a 2-molar solution of acetic acid? All right, so with this problem, we're going to just go ahead, Part A, categorize it. What kind of problem is Part A? What is the pH of a 2-molar solution of acetic acid? What kind of problem is it? Weak acid problem. So how do I start this? Rice table. So I'm going to take my weak acid, add it to what? Water. So HAC plus H2O, equilibrium with AC minus, go away, minus this thing. Oh, that'll work. Plus H3O plus. Water's not included. We know it's 2 molar, so 2.0 here, 0, 0, minus X, plus X. I'm being kind of in the way a lot on this one because I'm trying to write neatly for this video. So we have 2 minus X, trumpet, X, and X. So our Ka expression is going to be H plus times AC minus divided by HAC, which is equal to 1.8 times 10 to the negative 5th, X squared over 2.0. X, which is equal to the H plus concentration. And that's what they're looking for here. Compute the hydrogen ion concentration. So we don't even need to take it to pH. What do we get? Oh, no. Sorry. That's part B. We do need the pH. What is the pH? What's the H plus concentration? Can I get a second? 0.006 moles per liter. So our pH to 2 decimal places. 2.22. Are we good with part A? That's a review from last unit, right? So let's take a look at part B. A buffer solution is prepared. Doesn't mean we're starting out with a buffer solution. It means we're potentially making a buffer solution by adding 0.1 liter of 2 molar acetic acid to 0.1 liter of 1 molar sodium hydroxide. What kind of problem is this? We're adding acetic acid to sodium hydroxide. That's a buffer problem? No, that's what I was just saying. It says a buffer is prepared. That means that's what's done at the end. It doesn't mean what we start with. What are we starting with? It's an invader problem. Don't we have something strong to a weak acid? So what is our formula? What's our invader? OH minus is going to be added to acetic acid, our invasion equation. So what do we make? AC minus plus H2O. So to talk about the war, what do we need to convert those values to? Moles. So let's look at the sodium hydroxide. We have 0.1 liter of 1 molar. So how many moles do we have? 0.1 moles of this. HAC, we have 0.1 liter of 2 molar. So how many of that do we have? 0.2. Do we have any AC minus yet? Nope. All right. So remember, these are moles. So what are we going to run out of? OH minus. So we're going to lose 0.1, lose 0.1, and gain 0.1. So we get 0. This is 0.1, and this is 0.1. This is what's left over now. A buffer. And that's what they meant by a buffer solution is prepared. It's still an invasion problem. They told you that you should have a buffer left over at the end. What can you tell me about this buffer? Look at the values. 0.1, 0.1. Yeah, this is like our midpoint in a titration. We've got that final bit, pH is equal to pKa. This whole thing canceled out, right? So all we have to do then, you can see that. I'm okay with you just showing this. So pH then is equal to negative log of 1.8 times 10 to the negative fifth. So what is our pH? .74. Can you get a second? Yes. All right. Now, we were sloppy here and lazy, and we left this in moles. I'm not going to promise you that we're not going to have to go back and remedy that. Actually, I know we're going to have to go back and remedy this because of Part C. Part C says, suppose that 0.1 liter of 0.5 molar hydrochloric acid is added to 0.04 liter of the buffer prepared in Part B. We're not taking all of the buffer. We're not taking all 0.1 moles of these. We're only taking 0.04 liters of it, so I need the molarity of these things so I can figure out how many moles 0.04 liters actually is. So we have to go back to Part B. What was our total volume from Part B? We had 0.1 liter and 0.1 liter, right? Y'all have to check me. I make mistakes too. So 0.2. So we're going to divide both of these by 0.2. So what is my HAC AC minus concentration for all of this, these guys? 0.1 divided by 0.2. Let's go, quick. 0.5? Yes. 0.50 moles per liter. So that's the concentration of HAC and AC minus in that buffer. Okay. So I got to go back and read the next. Suppose that 0.1 liter, I'm just going to write this stuff down, of HCl, which is strong, H plus minus, is added to 0.04 liters of the buffer prepared. Compute the H plus ion concentration is what we're looking for. So this is Part C. All right. We are having another war. Just when they got done with another war, now a different alien comes in. It's like, come on. It's like, what's that movie I love, and I can't remember, the Ender's Game. It's like, they're coming back. H plus is our alien this time. What is it going to react with? AC minus to make HAC, right? Yes? Okay. So we got to do our war with moles. H plus, we have 0.1 liter, and I didn't write down the molarity. It's 0.5 molar. So what's 0.1 times 0.5? 0.05 moles of H plus. How many moles of AC minus and HAC do I have? I'm not using the full 0.1 from up here. I'm only going to take 0.041 or 0.04 or 0.041. 0.04 liters. All right, so what do? Multiply 0.04 times 0.5, and what do I get? 0.02 of this and 0.02 of that. So those are all our moles. How many moles are going to react? 0.02. So what's our situation now? Let's evaluate it. Strong winds. So we have 0.03 moles of H plus. Can we use the moles to find the pH? I need to convert it to what? Molarity. What's my total volume? 0.1 plus 0.04. So I divide this by 0.14 liters. So my H plus concentration, which is all I'm looking for in the problem, is what? How many sig figs are they rocking? Two sig figs. Can I get a second on that? 0.21 moles per liter. So do you see how problems are not necessarily difficult per se? It's just a matter of paying attention and really doing things a step at a time and not freaking out. They're very layered, okay? All right, let's do some more College Board. We're going to work until the bell, do as much as we can. 9. A 4-gram sample of sodium hydroxide is dissolved in enough water to make a 0.5 liter solution. Calculate the pH. What type of problem is step A? Strong base. Strong base. So if I'm calculating the pH, I need to find the concentration of OH minus. They don't give me concentration, of course they don't. That would be too nice. So I've got 4.00 grams of sodium hydroxide. What's my molar mass of sodium hydroxide? It's 40 grams. And then if I just want to keep this going and do moles over liters to get my molarity, that would give me molarity by dividing by 0.5. You know you can do that, right? You don't have to have something on top. Just look at the units. Moles over liters. That's how I passed physics in college because I didn't know what I was doing. I didn't have the Messages teaching me. Lucky bastards you are. All right, what do we get? Point what? 0.20 moles per liter. All right, so if I want to get if I take the negative log of that, I'm calculating what? POH. What is the negative log of 0.2? .699. So they want the pH of the solution, which is what is it? Let's do 2 sig figs. 3 what? Okay. All right. Part B. Suppose that 4 grams of sodium hydroxide is dissolved in 1 liter of solution that is 0.5 molar ammonia and 0.5 molar ammonium. Assuming there is no change in volume and no loss of ammonia in the atmosphere, calculate the concentration of the hydroxide ion. Okay, so what are we going to start with? You can do what you need to do. I'm recording. It's a war, so what are we going to start with? Right, but I want the invasion equation. What do we put first? OH minus And what are we going to be at war with? We're at war with a buffer, right? Which part of the buffer does it react with? NH4 plus. And then what are we going to make? Ammonia and H2O. Very good. All right. So we're going to do moles of each. How many moles of OH minus? We had moles from up here, right? 0.1. Ammonia, we have 0.5 molar and 1 liter, so 0.5 times 1 is 0.5 moles of this, 0.5 moles of that, and that goes away. So we have 0.5 moles of both of the parts of the buffer. How much are we going to lose? 0.1, lose 0.1, gain 0.1. So we have 0, and we have 0.4, and then we have 0.6, right? So what's left over after the invasion? A buffer, so we're going to use Henderson-Hasselbalch, but what kind of Henderson-Hasselbalch this time? The POH is equal to the pKb plus the log of the ion concentration over the base. So POH is equal to the negative log. The pKb, the Kb of ammonia is the same as the Ka of acetic acid, 1.8 times 10 negative fifth, plus the log. Are you cool with us not converting it to concentration now? Do we understand why? So the ion is what number of moles? 0.4 over 0. If I converted it to concentration, I'd be dividing both of these numbers by the same number, which wouldn't change my ratio, right? All right, so POH is, let's take it out to 2 sig figs. This is not our final answer, though. They want OH minus, so don't worry about sig figs yet. 569. So let's go ahead into 2 sig figs now. Our final concentration, 10 to the negative 4.569. 9.43 times 10 to the, what is 2.7 what? Times 10 to the negative fifth moles per liter. The question wants OH concentration, Marie. All right. How are we doing? Having a blast? Let's keep going. Ooh, it's a 4-part question. So exciting. A buffer solution contains 0.4 moles of formic acid, HCOOH, and 0.6 moles of sodium formate, HCOO minus. We're going to just deal with the formate ion. In 1 liter solution, the ionization constant, Ka, of formic acid is 1.8 E negative 4. Part A, calculate the pH of the solution. Yay, that's easy. What kind of solution are we finding the pH of? A buffer, so we're just going to plug and chug. pH is equal to the negative log of 1.8 E negative 4 plus the log. What's the concentration of the ion? Well, look, we're in 1 liter, right? So both of these are moles per liter. So the ion is what concentration? 0.6. The ion is 0.6. The acid is 0.4. So our pH, go ahead and give me 2 decimal places. Everything is 2 sig figs except for the liters. 3.92. So part A of these complex problems is always going to be pretty easy. All right. Part B, if 100 mils of this buffer is diluted to a volume of 1 liter with pure water, the pH does not change. Discuss why the pH remains constant. We did this yesterday. Yep. The concentration of the base and conjugate Or is it acid and conjugate base? It's acid and conjugate base. Are both diluted the same. And I'm just going to say their ratio, EIR? I can't even spell. Is it EIR or IER? Their ratio doesn't change. Therefore, pH stays constant. All right, part C. A 500 ml sample of 1 molar HCl is added to 100 ml of the original buffer solution. Calculate the H3O concentration. So, we're invading, right, with H+. What part of the buffer is the H+ going to react with? The acid? Is an acid going to react with an acid? No, it's probably going to react with the conjugate base, or the ion, right? And what is our ion? HCOO-. What does that make in the war? HCOOH. If you haven't figured it out yet, when you invade the buffer, the other component you make is the other part of the buffer. So we're going to, how much are we mixing? 1 molar, 5 mils, so that's 0.005 moles of this. How many moles? Now we got to go up. We're using 100 mils of 0.4 formic acid. What's 0.1 times 0.4? That's of the acid. And then we have 100 mils, 0.1 times 0.6 of this, 0.06. Are we good? Am I doing it right? Stop me if I make any stupid mistakes. So we're going to lose how much? 0.005 minus 0.005, and we're going to gain 0.005. And so I get 0.055, and then I get 0.045. So what do we have left over? A buffer. And luckily, it's Henderson-Hasselbalch, so we don't have to convert those stupid things to concentration. pH is the negative log. It's 1.8 e negative 4, yes. Plus the log of ion concentration. What is that? 0.055 divided by 0.045. Our pH is equal to 4.83. Do they want the pH? 3.83? I might have just misheard. 3.83. Our H+ concentration then, because that's what they want, to give me 3 sigafigs. 1.47. There's got to be an exponent. So 1.48. My God. Someone said 7.9, so I went 8. So what is it? Times 10 to the negative 4 moles per liter. Do we all agree with that answer? Y'all are freaking me out. Everyone got that? Okay. All right. We're not done yet. We have a part D. Part D, luckily, is independent. It doesn't depend on before. It says 800 mils of 2 molar formic acid is mixed with 200 mils of 4.8 molar sodium hydroxide. So first thing I want to do is write the invasion equation. What are we invading? Or is it an invasion? What are we doing? OH minus plus. It's just telling you, why are we quiet? We're adding OH minus to what? Formic acid, so that's HCOOH. So what is that going to make? HCOO minus plus water. And if you write COOH minus, it's fine. It doesn't really matter. So we need to invade. So we have 0.8 times 2. What is 0.8 times 2? 1.6. That's, oh wait, that's the formic acid. And then how much? 4.8 times 0.2. I can't hear you guys. 0.96. You guys are way too quiet. We don't have any any formate, do we? Nope. Are these numbers correct, and did I place them correctly? All right, so how much reacts? 0.96 plus 0.96. So we have nothing here. We have 1.6 minus 0.96, 0.64. And then this is 0.96. What do we have left over? Buffer, same system. Does it say, what do we want? The H3O plus again. I just want to stop at the pH. pH is equal to negative log of 1.8 times 10 to the negative 4th plus the log of what over what? 0.96 over 0.64. They're doing this to show you that it's not product over reactant, it's ion over, right? Looks like it's reversed from the other one. So our pH is equal to 3.921. They want the H plus. So to 2 sig figs, or to 3 sig figs actually. 3 sig figs, what is the H plus? -5 or 4? Did everybody get that? Okay. So you see how the problems have gotten pretty long? Yeah? All right, this last problem we're going to do. I want to do it because people, here's what students try to do. Oh, I'm invading propanoic acid with an acid. Do acids and acids react? Okay, so basically what happens in this problem is what? Strong winds here. If this comes into this system, the total pH is based on the H plus concentration from this one plus the H plus concentration from this weak acid. But because this is a weak acid, this is going to be basically mathematically negligible. So we're only going to need to find the concentration of the strong one and then take the negative log of it. That is it. All right? So they tell us we have 0.0250 moles of our H plus from the acid, and it is added to enough water to make 0.365 liters. And that gives us an H plus concentration of what? .0685 moles per liter. So what do they want us to find? pH to 2 decimal places. I lied. I want to do 3 because we didn't even use this number. So give me 3 decimal places. And there it is. So I did calculate in the last class. I just don't think we're going to have time because I didn't do another problem with them. I went and found using a rice table, I found what this was. And when I added it, it ended up giving a pH of 1.170. That's how much it changed it. And that's not enough to legitimately make you have to do all that extra work. Okay? So point being, don't try to make a reaction happen between things that don't react. Okay? You've got to watch yourselves and classify what you're doing. All right, invaders are done. Now we're going to spend the next few days practicing with titrations. Every titration, anytime you do a titration and add stuff from the burette, that's an invasion. You've let the calculator do all the calculating for you up until now. Now we get to do it ourselves.